Hi folks, this is Mod Zero and welcome to another video on the system design for URL shortener. So let's begin. The URL shortener is kind of a system that you can think of Bitly or TinyURL. So basically, the user will provide the long URL and our system should return this short URL. And whenever someone will open this short URL, we should redirect to the redirect the user to this longer URL. So for any system design, we should first mark what's the functional and what's the non-functional requirement. So basically, function is like the core features of our systems. So it will tell us what our system does. And the non-functional is like when we talk about the metrics. So it tells us how well our system should perform, right? So whenever we talk about any metrics, it is under a non-functional requirement. So let's discuss the feature first. So first of all, it should create a short URL from the long URL. Second, it should redirect our short URL to the longer one. So I have kept only these two basic features. Of course, you can add more optional features like the expiration time or maybe the analytics. But as for this video, I'm keeping it just simple. So for the redirect, whenever the user is providing the short URL, our system our system should look up this original URL and we should be having these two types of redirect. Either it should be HTTP 301 or 302. So basically 301 is like permanent redirect. So in this case, your browser and maybe the DNS, the caches the new URL, and maybe next time when the user is passing the same short URL, it will not hit your system. It will be using the cached value. Generally, this is used when there is a website migration or maybe a domain change. This type of redirect is used. But on 302 is like a temporary redirect, which means it's telling the browser that you have to again hit our service to gain the knowledge of the long URL. So generally in URL shortener, 302 is basically preferred because we want every time that each of the requests should be passing our system so that it will be our it will be under our control and we can change the destination later, and it's also useful if we are tracking the analytics, and it always comes in handy during debugging because the request is anyways hitting our server, and there we can use logging and we can track the request lifecycle, right? So this is why we prefer the 302 redirect. Now coming to the non-functional requirement, so we want the high availability system and it should be available at most 99.9% of the time. It should have low latency, like we are expecting around less than a 200 milliseconds, and this is kind of a we consider is quick, and it should be scalable to billions of users, and it should support 100 million daily active user, and definitely it should be fault tolerant. Now, talking about the entity, we will store the short URL with long URL and maybe some user data if we want, or maybe some another metadata. And for the API design, so this API is kind of a one-to-one mapping to all the core features that we have. Not necessary, but yeah, in most cases, it's like one-to-one mapping. So first, let's discuss on the creation of the short code. This will be like the post request, where in the body user can provide the long URL, and we will respond back the short URL, right? And the second feature was redirecting to the original URL. So basically, we will have a get API. User can provide the short URL in the parameter, and we will actually provide the response as a 302 redirect, and we will redirect to the original URL. Fine. So let us do some calculations and we will get the idea on how much larger scale we are talking about here. So as we have taken 100 million daily active users, right? Now we have two operations. One is the creation of the short URL and second is the redirect. Now definitely this creation of short URLs would be used much lesser and redirect feature will be mostly used. So I am expecting or I am assuming each user is using our service for let's say 10 redirects. So this will be 100 million into 10, which will be equal to 1 billion requests per day. Okay. And let's say creation of the short URLs. So I'm assuming here, let's say 1 million requests per day. Now this is like a write operation, right? Because it will eventually add a row in our database and redirect we are just doing a lookup in our DB, and whatever the original URL, we are just redirecting. So this is kind of a read request, right? So this is our average estimation here. And these things are also called back of the envelope estimation. So why we are doing it, we want to analyze the scale, and according to that, we will figure out like how much instance of the database or the cache or the servers we need eventually. Now let's say I want to continue this service for 10 years. So I want to calculate how much maximum storage I would be needing. So as we know, only the writes will increase our storage, right? So for storing 1 million requests per day, how much storage would be needing? That will be 1 million per day, and I want to calculate for 10 years, right? So 10 into 365, and that will be 3650 into 10 power 6 URL, which is eventually 3.65 billion URLs, right? So eventually we will be generating 3.65 billion URLs. Now to support this type of figure, what should be the length of our short URL that will be generating? So this short URL consists of how many characters, right? So we can store 0 to 9. We can store the smaller case alphabets, and we can store the uppercase alphabets. Example, you have seen on the TinyURL, right? It generates a short code like this kind of a string. Now, now the point is how many characters we should take that should support eventually the 3.6 billion URLs. So for that we have base 62 encoding, because the total number of characters that we can use are 62, right? So for one place we have 62 total combinations. So when you calculate 62 power 5, that will be 1916 million. So this is not covering our. When we do 62 power 6, now this can hold 56.8 billion combination. Now, now this can actually support our 3.6 billion URL requirement. So you can also eventually use log here. But yeah, so now as we know, we will be needing 6 character shortcode, right, to support our 3.65 billion URLs, right? So this conclusion is achieved. Now let's do the storage estimation. And to store this 3.65 billion URLs, how much storage would be needing? And we have designed our entity that we will be storing the short URL, long URL, and some of the metadata like user. So our short URL are 6 character long. So its size is 6. Maybe long URL we can take as 300 to 400 character. And there will be another metadata like user details or something. So on average, each of our DB rows will store the 500 bytes, right? So this would be enough to store our information of each row. So for one row is 500 bytes, then for total URLs, we'll be needing 3.65 billion into 500 bytes. I'm writing 500 as 1000 by 2, and this will be like approximately 1.8, and this is 1.8 into 10 power 12 bytes. So this is eventually 1.8 terabytes, which is close to 2 TB. Right? To support our total URLs for a period of 10 years, we will be needing 2 terabyte of storage. And also, we have seen the reads per day and the writes per day. So when we will calculate requests per second, so in one day, approximately 86,000 seconds are there, and we are approximating it to a lakh. So we are dividing 10 power 9 to 10 power 5, and we are getting 10,000 basically reads per second. Similarly, for write, we will having only 10 writes per second. So this type of scale, the two TTP data and 10,000 reads and 10 writes per second. So eventually this can be handled by a single instance database, right? And as we have only short URL and long URL lookups, so for that we can use any key value DB. And for this example, we can use the Amazon DynamoDB. Now this database can handle this type of scale in a single instance. So now we are clear about the capacity of the database. So as of now, we have decided this type of simple architecture. Like from the web browser, user will hit, let's say, the long URL. Our server will convert it to a short code, a short URL. We will discuss how we will convert it to a short URL in a minute. And this will be stored in our database, like a key value pair. So as you have realized, it is a read-heavy system, right? To reduce latency, we cannot always request a DB for each and every read request. So what we should do here, we should introduce caching. So we'll choose Redis for this because it stores the key value pairs directly into the RAM, right? So it will be very fast, right? And we'll be using the cache aside policy, which is also called as read through, which means we will check the cache first, and if it's a cache miss, we will check the DB, and the DB will provide the new key value pair back to the cache. Right. So basically, DB will update the cache eventually, and this is known as the cache aside or a read through policy. And for eviction policy, we'll be using the least recently used, which means that whenever our cache storage is full, we want to free up the space, right? So the least recently used shortcode will be deleted, and that is a least LRU eviction policy. Now, as we have done discussing the database and the cache, let's discuss on the main point, that is our application server, and how actually we will be converting our long URL to the short URL. For this, we can have many strategies. Let's discuss it one by one. So maybe we can hash the long URL and create a short code out of it. And for that, maybe we can use MD5 or SHA 256 hashing strategies. But the issue with this is MD5 is a 128-bit hash generator, right? And one hexadecimal character is 4-bit. So eventually it will be 32 characters. But what we have decided to generate as minimal shortcode as possible, and that was 6 characters. So this is not fitting in our criteria. And similar of SJ256 also, this generated 256-bit character. So definitely it will not work in our criteria. So further, what we can do is we can use a counter approach. We know that we are using the base 62 encoding for this shortcode character, right? And you can convert any decimal number, which is a base 10, to a base 62 encoding, right? For example, we need to convert this decimal 1000 to base 62. So we generally follow this method. We divide the 1000 with 62 and we calculate the remainder and we convert it upside down, right? So 0 to 9 will be 0 to 9 character, and then we will be having the A to Z. That's why the 16 is getting mapped to G. So eventually we get this encoding, let's say G8 for a number which is 1000. So for the ID generation, we can rely on the server here for the counter, because if you're thinking about the ID generated from the database, so basically key value database, NoSQL database doesn't support the auto increment IDs just like the SQL one. So for the generation of unique counter, we can have a counter service here which this server will use, right? Let's say for the first it will be 2, 3, and eventually it will be going on, right? And this ID will be eventually converted to the shortcode. And if you are having one fusion, right? Let's say this is only 2 character and we have thought of 6 character, then we can add a padding anyways. Like for example, we can do a G8 and the rest will be the padding, right? So this will be the shortcode of this 1000 ID. Now the problem with this approach is we are having a 10,000 requests per second for a read request, and in peak it can eventually go up to 50,000 requests per second, right? So, the issue is one application server will not be feasible to handle it, and on an average EC2 instance or any 4-core server can easily handle up to 1000 to 2000 requests per second, right? To even support the average request per second, you will be needing 5 to 7 application servers, right? And then this counter would be an issue, right? Because let's say you have a counter at every application server. Now this server needs to be in sync because they want a unique number every time for each and every request. And there can be an issue if there is a request for a long URL and this counter has generated 1,000, and that time let's say this was 999. Now for 1,000 it will eventually add the shortcode in our database, but if another request will go to this server, this will be +1, and for any other URL it will be the same ID, right? So for two different long URLs you cannot have two same short URLs, and that would be a collision. Definitely there will be a load balancer, right, which will basically route the request to a different server on a round robin or maybe any other strategy. So how to resolve this issue? So maybe we can have another Redis instance or maybe the same instance which can act as a global counter. So in this case, each application server would be requesting a new ID from the global counter. And this Redis has an auto increment, which is an atomic integer increment, and it is also single threaded, so there is no no stress of the race condition. But again, there is a problem, which is latency. Now, for each and every request, each server has an additional API call to our Redis instance, which will eventually be passing a counter value. And also, this is a single source of failure. Now, if you want to prevent this, then again you will be needing to have a replicas of this counter, and then again there will be a sync issue. So this solution also is not up to the mark. Instead, what we can do is, instead of this server requesting the counter every time, maybe we can assign some ranges here, right? For example, this application server, it will generate a range from 0 to 1 million. This will generate a range from 1 million to 2 million, and eventually you will be having several other servers, right? So this will prevent us to have synchronization in any global service or an additional network call for a global counter. And also it will handle the collision because there will be no overlaps in these ranges, right? If it is including 1 million, it will be 1 million plus 1, right? There will be no overlap. So basically, to assign these ranges and handle the configuration management, we use Apache Zookeeper. So as you can see, now each of our server, it is coordinating with the central Zookeeper service for getting a new range, right? So each of these ranges will be assigned to our different nodes, and Zookeeper will keep the track of it. And maybe if any service goes down, then it can reclaim the same ranges after that. And Zookeeper will be managing all this. And therefore, once our service gets the counter, then it will convert it to a base 62 encoding string, which will be our final short URL. And this short URL will be then saved in our database, right? But also, here our database, which is a single instance database, can also be a single point of failure, because if database fails, our whole application would be down. For that, we can create the replicas here, and this will be our primary DB, and the replicas would be our secondary. So even if one instance fails, one of the replica can be selected as a leader, which will then serve the request. And also, as this is a very read-heavy system, so all three of the database can serve the read request, and only our primary database will be handling our write request. So it can also have a eventual consistency all around the replicas, right? So even the 10,000 read requests per second, or maybe during the peak time, if it crosses the 50,000 reads per second, all our three instances can work to serve those requests. So this is also adding the availability, and it's also handling our peak request time, right? So this will be overall our the high level design of the URL shortening service. So yeah, that's all for this video, and thanks a lot for listening.